Welcome. Many of us here build and deploy machine learning models. We think in terms of inputs, outputs, training loops, and inference endpoints. But the field is rapidly moving beyond static models that simply classify or predict. We're entering the era of AI agents. An agent is more than just a model. It's an autonomous entity that perceives its environment, reasons about its goals, and takes actions to achieve them. Think of it as the next layer of abstraction. While a model might identify an anomaly in a log file, an agent would perceive that anomaly, reason that it indicates a potential server failure, and then act by spinning up a new instance and rerouting traffic. This perception, reasoning, action loop is the fundamental difference. In this deep dive, we'll dissect this concept, moving from the foundational theory to the practical architectures you can build and deploy today.
To build robust agents, we first need a formal way to describe their purpose and environment. The classic framework for this is P's: performance, environment, actuators, and sensors. It's a simple but powerful tool for system design. The performance measure defines success. Is the goal to maximize trading profit, minimize server downtime, or optimize a supply chain? The environment is the world the agent operates in. Is it a simulated stock market, a Kubernetes cluster, or the physical world via robotics? Actuators are the tools the agent uses to affect change. Think API calls, robotic arms, or terminal commands. And finally, sensors are how the agent perceives the environment: system metrics, market data feeds, or camera inputs. Defining the P's framework before writing a single line of code forces clarity on what you're actually building. It's the blueprint that separates a simple script from a true autonomous agent. Early architectures, like simple reflex agents, map sensor data directly to actions, while more complex model-based agents maintain an internal state of the world.
So how does an agent decide on the best action? This is where the learning and reasoning engine comes in. A simple goal-based agent might use search algorithms like A* to find a path to a known goal. But the most dynamic and powerful agents are learning agents. They improve their performance over time through experience. The dominant paradigm here is reinforcement learning. An RL agent learns a policy, a mapping from a perceived state to an action, by receiving rewards or penalties from its environment. It's not just about the immediate reward. It's about maximizing the cumulative reward over time. This involves learning a value function, which estimates the long-term value of being in a particular state. For MLOps professionals, this introduces new challenges. We're no longer just deploying a static pre-trained model. We're deploying a system that learns online. This requires robust pipelines for continuous training, sophisticated monitoring to detect policy degradation, and simulation environments to safely test new policies before deploying them into production. The true power of modern agents, especially those based on large language models, is unlocked when they can interact with the outside world beyond their pre-trained knowledge. This is accomplished through tool use. An agent can be given access to a suite of APIs, a calculator, a search engine, a code interpreter, or your company's internal knowledge base. The React framework, which stands for Reason and Act, is a brilliant example. The LLM generates not just an action, but a reasoning trace explaining why it's choosing that action. For instance, I need to find the current CEO of company X. I will use the search tool. It then executes the search, observes the result, and reasons about the next step. This makes the agent's behavior interpretable and far more powerful. We can extend this further into multi-agent systems, where specialized agents collaborate. Imagine one agent analyzing market data, another executing trades, and a third monitoring system performance, all communicating to achieve a shared, complex goal. This is how we build truly sophisticated and resilient autonomous systems.
We've journeyed from the foundational P's framework to complex, tool-using, collaborative agents. The key takeaway is this: we are shifting from building ML models to architecting autonomous systems. For data scientists and ML engineers, this changes our role. Our focus expands from model accuracy to system reliability, observability, and security. How do you monitor an agent that's constantly learning? How do you prevent prompt injection or ensure an agent doesn't take catastrophic actions in a production environment? These are the critical engineering challenges. The opportunity is immense. We are on the cusp of building systems that can manage complex infrastructure, accelerate scientific discovery, and create highly personalized user experiences. Your challenge now is not just to be a model builder, but to become an architect of agency, designing the resilient, observable, and trustworthy intelligent systems of the future.